Lesson on electric force. But first, let's talk about the force we're most familiar with, the force that weighs us down every day, the force of gravity. Back in the fall, we studied a simplified version of Newton's law of universal gravitation, which he figured out in 1687. We were able to calculate the force of gravity as equal to our mass times the acceleration due to gravity, where g is 9.8 meters per second squared. But where does this 9.8 meters per second squared number come from? Well, the force of gravity on me is exerted by the Earth pulling on me. That is, it's the mass of the Earth exerting an attractive force on my mass. The larger my mass is, the more the Earth's mass will attract me. Thus, the force of gravity is directly proportional to the masses. We would say that the force of gravity is directly proportional to the mass. Newton also realized that the farther I am away from the Earth's center, the less the force of gravity can pull on me. That is, if I were to hike to the top of Mount Everest, the Earth would not be able to pull as hard on me because I would be much further away than the Earth's center. That is, the force of gravity depends inversely on the distance away from the center of the Earth. We can see here that the force of gravity is proportional to the inverse of the distance away from the center of the Earth. Newton made this an equivalence by saying that the force of gravity is equal to the mass of the Earth times my mass divided by the distance between our masses squared. And to really make this equivalence, you need a constant of proportionality, which he called big G, the gravitational constant. Looking further at this relationship, we can see that big G times the mass of the Earth divided by r squared is actually equal to the acceleration due to gravity, or 9.8 meters per second squared. But gravity is only one of the many fundamental forces in nature. Let's take a look at the electric force. Just about 100 years later than Newton, Charles Auguste Coulomb came up with a relationship for the electric force, but not between masses, but between two charges. Unlike gravity, charges can either be both attractive or repulsive. Coulomb recognized that the bigger the charges, the bigger the force. That is, the electric force also depended directly on the amount of charge. That is, if I increase the amount of one charge, say Q2, the electric force would also increase by the same amount. He further observed that if you increase the distance between the charges, that the electric force actually decreases. That is, as the separation r increases between the charges, the electric force decreases, thus an inverse proportionality. Putting this all together as an equivalence, Coulomb wrote that the electric force is equal to the amount of charges, Q1 and Q2, divided by the distance apart, squared, but also including a constant of proportionality K, the electric constant. This now gave physicists a better understanding of two of the fundamental forces in nature, the force of gravity and the electric force. We'll see in class soon how these two forces compare. Even though they look very similar, that is, both the electric force and the force of gravity are inversely proportional to distance squared. Their differences in strength makes them very hard to unify. More on that later. Let's take a look at how we can determine the electric force between charges using Coulomb's law. Let's take a look at a practice problem here where we have two charges, Q1 and Q2, separated by a distance r. Recall that the electric force between these two charges, Q1 and Q2, is given by Coulomb's law. That is K times Q1 times Q2 divided by R squared. What now happens to the electric force if you double one of the charges? That is, we make Q2 double the amount, or 2Q2. Well, recall that Coulomb's law states that the electric force between these charges is directly proportional to the amount of charge. So you could guess that the new electric force will be twice that of the original electric force. But let's write it out in terms of Coulomb's law. Electric force equals K times Q1, and in this case, 2Q2 divided by R squared. If we just bump that 2 out to the front there, we can see we have 2K Q1 times Q2 over R squared, where this KQ1 Q2 over R squared is just the original electric force. That is, the new electric force is 2 times the original electric force. Here's another practice problem. Again, recalling that when Q1 and Q2 charges are separated by distance R, the electric force is given by K times Q1 times Q2 over R squared. Now, what happens to the electric force if you double the distance between the charges? That is, we move Q2 to twice the distance away from Q1, or 2R. If you remember, Coulomb's law says the electric force depends inversely on the separation between the charges. So if this separation increases, we could predict that then the electric force is going to decrease. But let's write it out in terms of Coulomb's law. That is, the electric force equals K times Q1 times Q2, our two charges, now over 2R squared. If we do the math out here, we have KQ1, Q2 on the top. 2R squared is actually 4R squared. So we can see now that here's our original electric force, KQ1, Q2 over R squared, and we have this extra 1/4 here. That is, the new electric force is a quarter of the amount of the old electric force, because the electric force depends on the inverse of the distance squared. Thank you for watching, and see you in class.